Today's speaker is Doug Greger. Doug is from Indiana University, and he's one of the leading experts on generic programming and related issues. Today he's going to be talking about one of the major features that's going to be added to the new version of C++. It's the word that everybody who works on this feature uses to describe it is concepts, and if you don't yet know what that means, Doug will tell you. And one reminder, this is being recorded and it's going to be going out externally on Google Video, so if you have any confidential questions for Doug, please save them until after the talk. Thank you.
Thank you, Matt. So I'm going to talk about concepts, and this is an extension to the C++ template system to support the programming paradigm of generic programming. So a brief outline of our talk. We're going to talk about generic programming. What is this paradigm? What is it used for? And where have we seen this before? Then we're going to go directly into concepts, this new language feature, and talk about all the various parts of this feature, how you're going to use it, try to give you a sense of what programming using templates and concepts is going to be like when C++ OX, the next version of the C++ standard, is actually here. And finally, we're going to tell you where we are with the formulation of concepts and the standardization efforts that are going on. So we start with generic programming. Now, generic programming is a methodology for building software. Specifically, it's a methodology for building reusable, efficient software libraries. We're very focused on libraries. We call them generic libraries. And there's three primary tasks when you want to build a new generic library. The first task is you want to categorize all of the abstractions in your domain. So if you think of your domain as linear algebra, what are the abstractions in that domain? Well, we have matrices and we have vectors. Now what we do is we describe these in terms of concepts. What concepts do is they describe abstractions. So they're our core for reasoning about entities within the domain. The next thing we do is we implement generic algorithms based on these concepts. Now the algorithms are generic because they work with any data type so long as that data type meets the requirements of the concepts. And finally, we build concrete models of these concepts. These concrete models are essentially real data structures and that meet all of the requirements of the concepts and therefore can be used with the generic algorithms. So in a typical library that's non-generic, you'll typically have essentially the models. You'll have data structures and you have algorithms that work on these data structures. In a generic library, you have a level of indirection between them that is the concepts. And that's where we get the extensibility of a generic library. So there are several characteristics of generic libraries that set them apart from other non-generic libraries. The first is that generic libraries are much more reusable than non-generic existing software libraries. So think about using a library. Typically what you have to do is you look at the library, you instantiate its data structure, copy your values into its data structure, and then run one of its algorithms on its data structure. With a generic library, this is not the process. The process is you take your data structure, you map it into the abstraction, into the concepts described by the generic library, and then you apply its generic algorithms directly to your data types. So a generic library is characterized by reuse of existing user-defined data types within their algorithms and their framework. The second characteristic of generic libraries is that they're composable. You can take one generic library from here, perhaps for one domain, and another generic library, maybe from another domain, maybe from the same domain, and you can map the abstractions of one over to the abstractions of the other. So essentially, you're taking two libraries, combining them together, and you can use them together in your program. The idea of generic programming is to make this seamless. So you can easily take libraries from many sources and make them work together. Efficiency is the final point. Generic libraries are built to be efficient. Efficient in this sense means we want the performance of these generic libraries to be on par with a hand-coded implementation for a specific data structure. If you use a generic algorithm and it's the same algorithm as a concrete algorithm, that generic algorithm should be as fast as the hand-coded implementation. The reason is purely pragmatic. If it's not as fast as the hand-coded implementation, people continue to use their hand-coded implementations. We won't get the reuse or the composability that generic libraries are intended to provide. So how do we get to a generic library from nothing or from an existing non-generic library? The way we do this is the process called lifting, and it's central to the generic programming methodology. Now, it's an iterative process. What we do is we start with concrete implementations. Say we have a handful of quicksort implementations. Maybe one sorts arrays of integers, and the other one sorts vectors of strings. Now, these are two different implementations, but we want to study these two implementations and try to determine how can we unify these implementations. Lift away specific requirements, for instance, that we need an integer here or a string here, and try to write something more abstract, a generic algorithm that covers the behavior of these concrete algorithms by placing fewer requirements on its input parameters. For example, taking these two sort algorithms, why not write a sort algorithm that works on arrays of any type t, so long as t actually has some partial ordering on it that allows us to sort. Now, when we have these requirements, like t has a partial ordering on it, we bundle these requirements into concepts. These are the abstractions of our domain. It's how our domain works, how we talk about it. Now, as I said, lifting is an iterative process. We continue lifting, looking at generic algorithms, looking at concrete algorithms, and building more and more generic algorithms until we get to something that essentially subsumes the functionality of many, many different concrete implementations. And in doing so, gives you the same performance back that you would get from any of those implementations when used with a specific data type. And finally, there's usually something beautiful in a truly generic algorithm. It fits like the mathematical description of an algorithm. It says exactly what the algorithm is, but without tying down any of the details that are necessary to make something implementable in a non-generic context, but you can leave them unspecified in a generic context so that the user can provide them when using your generic library. If you recognize the picture of Plato, it's because we're all Platonic idealists at our hearts, and we're searching for the higher truth and the beauty of the abstraction in our generic libraries. Still, let's get a little bit more concrete and talk about the C++ standard template library. Now, this is the first generic library that really became widespread in its acceptance. So it became part of the C++ standard in 1995. C++ standard was released later on. And what the standard template library did better than other libraries is it built three different kinds of components that are all different kinds of abstractions. So we have the container abstractions. Now, the containers in the STL are, of course, lists and decks and vectors and maps and sets. There are many different containers, all of which meet these requirements of the container abstractions. There's also the algorithm abstractions. These are the generic algorithms, sorting algorithms, searching algorithms, et cetera, that are part of the standard template library. Now, the way these containers and algorithms interact is not directly. We don't write a sort algorithm on a vector. Instead, we use this in-between abstraction called an iterator. Now, an abstraction, the iterator abstraction abstracts away the notion of walking through a sequence and looking at all the values in it. So the generic algorithms within the STL are described in terms of iterators, so they work on any sequence of values. The containers in the STL provide iterators that can be passed to the algorithms. So you can take any container and use it with any algorithm in the STL, and it just works. In addition, you can create your own containers, meeting the requirements of the STL, and use those with the STL algorithms, or create your own STL algorithms and run it on the existing containers. So we get a lot of reuse by building these separate abstractions, particularly with the iterator abstraction to abstract the notion of data access. Now, performance in the STL has always been a very large concern. And so Alexander Stepanov built these abstraction penalty benchmarks, which are used to test compilers to ensure that they're doing the right optimization so that the abstractions of the STL cost you nothing in terms of runtime performance. Remember, performance is key for generic programming. The abstraction penalty benchmarks help us achieve that in the world of C++. Now, because of the success of the STL, many libraries have followed this generic programming paradigm in C++, and generic programming has been very popular in C++. It's been very successful. The reason is that C++ templates are an extremely powerful mechanism for describing polymorphism, for describing abstractions. Now, combined with user-defined classes and overloading, that allows us to write generic algorithms that can work on built-in types just like they work on user-defined types. So it allows us to build very, very rich generic libraries, and many have been built. You can go look on the web to find many of them. One of the keys that made templates work for generic programming is the instantiation mechanism. When you use a template with a specific type, the compiler instantiates that, meaning it creates a new copy of that template optimized specifically for that type. That's where you get your performance. That's why the STL actually works. Now, if the situation were perfect, of course, we wouldn't be talking about extending C++, and there are significant problems. The first problem is that we can't directly express the ideas of generic programming. We can think about them, we can write down concepts in documentation in the abstract sense, but when it gets down to C++ code, we're essentially using features and tricks of the template system to make these things happen. There's a huge cognitive disconnect there. Partially because of this, and because of the many template tricks that have been found to help express generic programs, generic libraries written in C++ are very fragile. We want to actually see what this means. So here is a very, well, relatively simple find algorithm written in the style of the STL in C++ today. So we have a template, it has two type parameters, Input Iterator and T. Now the name Input Iterator tells the human reader that, well, we want that type there to be an input iterator. It's a kind of abstraction in the STL. It doesn't tell the compiler anything. And what happens is that the compiler will look at this template and it'll accept it. And perhaps we're going to test this template, so we're going to call find with a vector. It works. Wonderful. Well, now we have, using the iterator abstraction, we have a generic algorithm, and we can call it with the container of our choice. Okay, there's also a list type, and say we want to call find with a list. Does it work? Well, no. From the documentation, it looks like it should work because lists produce bidirectional iterators. Bidirectional iterators are input iterators, and up here at the top, well, it looks like it works. The problem, however, is here we have this first is less than last terminating condition, use the less than operator. That works wonderfully for vector iterators because they actually have a less than operator that orders them. However, it doesn't work so well for list iterators which don't have a less than operator. And so what the user is going to get back from making this mistake is an error message that says, in the implementation of this find algorithm, you don't have a less than operator. What happened here? Well, what happened is that the person that wrote find was wrong. He should have used not equal instead of less than. That's fine. But the error wasn't caught until some unlucky user tried to use it in a way that wasn't the specific way that this algorithm was tested. That's the fragility problem of C++ templates today for generic programming. There's no way to tell who's accountable for an error. Is it the person that wrote the template or the person that used the template? You don't know because the error messages you get back combine both contexts together. So the question is, can we design better support for generic programming in C++, extending templates, to fix the fragility problem, to make it possible to describe generic programs and generic libraries the way we'd like to describe them, using the abstractions we think about, but without sacrificing any of the great things the templates already do. They give high performance, and they're extremely flexible. So with this in mind, we set out with these specific goals. We want to support all of the ideas of generic programming in C++ directly. The way a generic library is documented, we want to be able to write that in actual code and have the compiler help us out. Second, when we add this concepts feature to C++, we want to get modular type checking. By that, we mean that when you actually write a template, like the find template, the compiler is going to do complete type checking at the time that you define that template to ensure that things are correct with respect to the requirements of the template. If there's a problem at that point, the author of the template should get an error. On the other side, when a user uses something like the find algorithm, the compiler should check, do you meet the requirements of this find template? Do you meet the requirements of this generic algorithm? And if so, everything should always work. It should instantiate properly. You should get no horrible error messages. Now, if the user made a mistake in the call, they should get a nice error message telling them that you don't meet these certain requirements of the generic algorithm. Please try again. When we make these changes to C++, we need to keep the performance exactly where it is. C++ programmers are accustomed to excellent performance from C++ templates. We can't change that, otherwise we're creating a performance safety trade-off that never goes well for programmers. Also, backward compatibility is a very strong constraint. There's millions, billions of lines of code out there that use the C++ template system just like it is. We can't change those. We can't break that code. That's the easy backward compatibility part. The tougher part is that there are a lot of generic libraries out there that could benefit from being evolved toward using this new feature of concepts. Now, if you evolve these libraries, those libraries change, that's fine. But we like all the code that uses those libraries, like the users of the standard template library, their code should continue to work even if the underlying generic library has changed. That's a much stronger backward compatibility constraint. Now, we're adding to C++, which is a large language. We're adding new features, and yet we want to make it simpler. Seems like a paradox. How can you add something and also make it simpler? Well, the reason we think that we can make it simpler is that many of the ways that people use templates now are tricks. They're complicated tricks. You can't even read them in a book in many cases. You have to go dig through newsgroups to see how they work, or go look at the Boost C++ libraries to see what those guys did. Right? It's a lot of tricks. It's not really language knowledge, it's language trick knowledge. And that's why templates are very hard to use right now. We're replacing a lot of those ideas with new ideas based on the concept system that you can express directly what you mean rather than fooling the system into doing what you want. So the end result should be very simpler and much simpler. And when you're using templates, you won't need to know any of these tricks anymore. You just need to know the actual language features that you want to use. The final goal is we don't want concepts to be some academic idea that's played with once and tossed away. Concepts are intended to go into the upcoming ISO C++ standard. We call it C++ OX because it's supposed to be finished by the end of this decade. And it will be a major new feature within the language. So let's move to the actual concepts themselves. So there's essentially 3 interlocking features that define the concepts extensions to C++. The first is concept definitions. So here we want to state what is a concept and what are the requirements that it places on its types. This allows us to describe the entities in our domain, that first part of writing a generic library. The second part is where clauses. What where clauses do is they specify constraints on the template parameters to a given template, function template. For instance, the find algorithm had no description of what the actual type parameters need to do except in the documentation, the names of those parameters. What you can do with concepts is you can add a where clause that states explicitly what concepts those types need to meet for the template to work properly. And finally, there's concept maps. Now, what concept maps do is they map the real world of existing data structures and built-in types into the domain of concepts. So you can state how your particular data structure meets the requirements of a concept. Now, we'll actually start in the middle and take a look at where clauses. Now, today's templates are essentially unconstrained. There are no constraints placed on the template parameters. So concepts introduce a new kind of template called a constrained template. A constrained template is essentially a template like this min here that has a where clause. Now, here we have essentially the simplest of generic functions. It takes the minimum of 2 values. Those values are of type T, and T can be anything so long as T meets the requirements of the less than comparable concept. So where less than comparable T limits the applicability of this template to types T such that they are less than comparable. Once we have that, we've enabled modular type checking. That is, the compiler is going to type check the body of this function against the where clause to make sure it will always work properly. And on the other hand, when a user calls into this function, if they try to give some function T that doesn't have a less than operator, the compiler will reject the call to min and say, you don't meet the less than comparable concept. So let's take a look at less than comparable. We've seen a generic algorithm. Now what we need to see is the actual concept behind it. So here's the less than comparable concept. We declare it with the concept keyword. This is a new kind of entity in C++. And less than comparable has a single template type parameter called T. In the body of this concept, we list all of the syntactic and semantic requirements that need to be met for T to meet the requirements of this less than comparable concept. So for T to be less than comparable. On the first line, we have this operator less than. What this states is that there needs to be a less than operator somewhere that takes 2 T's, whatever those T's are, and returns a Boolean value. The rest of the constraints are semantic constraints. So here we state the axioms irreflexivity, asymmetry, and transitivity. We say, for instance, for the less than comparable concept to match, well, x cannot be less than x. That's a basic property of less than comparable. And so within these concepts, we state all of the requirements that types need to meet. Okay? This is categorizing our abstractions. Now, there's other kinds of requirements you can write. For instance, you can write member function requirements if you'd like to. So here we have a copy constructible concept. If a type T is copy constructible, it should match this concept. And we can write member requirements here that say T needs to have a copy constructor, written this way with the T::T syntax, and it needs to have a destructor. Of course, you can write in other requirements for member functions if you like, or free functions, or operators. Essentially, any kind of functional requirement can be described within a concept. Now, these two concepts have had a single type parameter. We've always called it T. However, we can parameterize concepts on many different parameters. Why not? So here we have an equality comparable concept that's type asymmetric. It has two type parameters, T and U. They can be the same, they can be different, doesn't matter. And in the signatures, we're always comparing a T on the left-hand side to a U on the right-hand side. Okay. And of course, the syntax extends naturally to any number of parameters, so does the semantics. So let's take a look at some more interesting concepts. So the iterator concepts are what really made the standard template library a great library. So what we need to do is be able to express those concepts in terms of the concept mechanism. Now, an iterator abstracts the notion of iterating through values of a sequence. You usually have two iterators, a begin and an end iterator, symbolized by these arrows on the left and right of the screen at the bottom. And the begin iterator points to data, and you can move it along in steps. The end iterator points one past the end of the data. This is how we signify the end of a series. And so what are the operations we actually need to be able to describe the abstraction of an iterator? Well, we have a concept input iterator, has one type parameter, iter. We have pre-increment and post-increment operators. In C++, we use ++ to move forward. So we describe those. We need equality and inequality so we can test two iterators, see if we've hit the end of a sequence. Again, these are just signatures we write in the concept body. And finally, we get to the dereference operator, the star, like dereferencing a pointer. And we come to a question. What type is returned when we dereference an iterator? Well, it depends on the iterator. If it's a pointer into an array of integers, like this example here, well, then the type that we return is actually an int. But we could also have a list of floating point numbers, and then the value type here, the thing that we return, would be a float. The way we describe this in the concept system is through what we call associated types. Now, these are essentially type parameters that are nested in the body of the concept. So they vary as the concept varies. And so here we state that every iterator, so every type that meets the input iterator requirements, has a value type associated with it, and that's the type that's going to be returned from the dereference operator. Next step, there can be many associated types with any given concept, and so here we call out one of the other common types, which is the difference type. So there's this pointer, this iterator at the beginning of our sequence, and that iterator at the end of the sequence. How do we measure the distance from one to another? Well, the difference type is an associated type of iterators that allows us to express this distance somehow. We don't know what the difference type is. It varies from one iterator to the next. If your iterator is just pointing into an array, well, then it needs to be big enough to represent the difference between addresses in your machine. If it's pointing into some large file system, well, maybe it needs to be a much larger type. What we do know about the difference type of an iterator is that it has to meet the requirements of the signed integral concept. So it needs to be an integer-like type that can be both positive and negative. So we can express this within our concept mechanism via a nested requirement, which is a where clause inside the body that states essentially how these associated types need to behave. Armed with this, we can actually look back at a real generic algorithm. So we talked about find earlier. Well, let's look at a find that's implemented using the concepts mechanism. So again, we've written a template. It looks mostly like an existing C++ template where we have type parameters iter and t. We take in several parameters. We loop over all the values, searching for the value that the user asked for. Except now we have this where clause. We say that the type iter needs to meet the requirements of the input iterator concept. That's part one. That allows us to iterate over the sequence. Part two is this equality comparable concept. because we have this expression, star first equals value. So we're dereferencing the iterator, comparing that result against the value the user passed in. So therefore, what we need is the value type of the iterator, written with this nested type syntax here, to be equality comparable with the type T. And given this definition, of course, the compiler can completely type check this separately, and we'll get better error messages out of, say, this formulation than the first formulation, which didn't use any of these templates.
You don't have to say type name, input iterator, iterate, call value type.
You do not need to say type name. So I mentioned simplicity and making things easier. That's one of the cases. Now, the reason you don't have to say type name is because input iterator is a concept. Concepts aren't like classes and specializations. So inside a concept, if we say value type is a type, it is always a type. Input iterator of anything, : value type is always a type. Compiler knows that, so you don't need the type name keyword. Matt.
You also mentioned backward compatibility. If you had not been worried about backward compatibility, would you have written this in exactly the way that you have here?
Possibly not. And I think you highlighted my next move.
Okay.
So ignore the where clause and look at just the code in the red box. That's today's templates. This works. Right? This is the code that you can go into your C++ standard library implementation. You'll find something that looks exactly like this, modulo naming. And so part of backward compatibility is isolating the changes that we make so that, for instance, this where clause, which describes all the requirements, that could be inside a macro of some sort, such that when the macro is one way your compiler supports concepts, you use the full concept-based version. If you have an older compiler that doesn't support concepts, preprocessor strips it away, you get an old template that works as it always did. Backward compatibility is extremely important, and by isolating things in this manner, keeping the where clause separate, we can get better backward compatibility than we otherwise could.
Is it an error to use the word type name?
No, it's not an error to use the word type name. It's easier that way for transitioning people that are used to writing type name in front of all these types. Even I write these type names all the time, and it's better for backward compatibility also if you can write that type name in there. It's just ignored.
Also, if you forget to do the very quality comparable, can you get an error out of that?
Yes, you'll get an error message when you write this template that says, I can't compare star first to a value. We'll see that a bit later in the talk, where we actually look at some error messages from our implementation. So the last piece of the puzzle is the concept maps. And for this, let's consider a call to find. And we're going to call find with integer pointers. Now, for this call to succeed, we need to make the call, and then we need to know that integer pointers are input iterators. Does the compiler know this by itself? Maybe, maybe not. In essence, it's going to be no. And so what we use is a concept map that tells the compiler, yes, my type, integer pointer, meets the requirements of the input iterator concept. The concept map tells it that it does meet the requirements. The body of the concept map tells how it meets those requirements. So in this case, remember the input iterator concept had value type and difference type associated types, and those differ from one iterator to the next. So we state them as type defs inside the body of the concept map. We say for an integer pointer, the value type is int and the difference type is pointer diff t. Now the compiler knows how to make an integer pointer into an input iterator, and the call to find up here, our constrained find, will succeed. Now this sounds very tedious. What if you have floating point pointers? Do you have to write another concept map? Well, yes, but why not go for more abstraction? Why not turn this into a concept map template? So any pointer to any type t meets the requirements of the input iterator concept. The value type is t now, because it depends on what that template parameter is. And the difference type, of course, is still pointer diff t, because that's how you measure pointer differences.
I'd like some clarification on this value type and difference type.
Sure.
When you initially applied it to an iterator of a vector, is the value type in the concept the same thing as a value type inside the vector class, inside the vector template, or?
It should be, yes.
So there used to be, suppose the definition of a vector did not have a type def for value type, what would happen?
Then you could put the definition of value type inside the concept map itself.
And you can define it for classes or existing templates or whatnot?
Sure, yep. One of the most important features of concept maps, and we'll see this a little bit later, is that you can write them without changing the concept. We didn't touch the input iterator concept, and without changing the types. We didn't change built-in pointers because we can't. We'll see where that becomes really important in a couple of slides. Now, back to building concepts. We built the input iterator concept, but the standard template library actually has a rich hierarchy of concepts. There are many different kinds of concepts. For instance, there's bidirectional iterators. They can move forward, like an input iterator. Actually, they can do everything an input iterator can. They can also move backward with a decrement operator. So to describe this, we use what's called concept refinement, which is essentially like inheritance of concepts. So here we can state that the bidirectional iterator concept on a single type parameter iter is an input iterator through this refinement syntax, same as C++ inheritance syntax, except that it has these extra operations. It has the pre-decrement and post-decrement requirements inside its body. So we write this little hierarchy on the right-hand side because every bidirectional iterator is an input iterator and can be used as an input iterator. We can go even further, of course. There's something called a random access iterator in the standard template library that can jump around. You can move an arbitrary number of steps in one constant time operation. What is a random access iterator? Well, it's a bidirectional iterator, again, refinement, with other operations. So here I've added the operator plus that takes an iterator, adds some value, some difference type onto it to jump forward, and then returns the resulting iterator. And now we've built an interesting hierarchy of concepts here where every random access iterator is a bidirectional iterator, is an input iterator. This allows us to classify all the iterators in our domain in different ways, but they all fit into the same conceptual hierarchy. Now, this refinement actually has a lot of power when it's combined with overloading. So here's a very simple operation on iterators. We want to take an iterator, x, and move it forward n steps. How do we do that with an input iterator? Well, we write a slow linear time loop that just steps through x while decrementing the counter n. Very simple, but with a random access iterator, this of course isn't the best approach. Random access iterators have a better way to do this. It's that plus operation we saw as part of the random access iterator concept. So we can write another advance overloaded with the first, has the same signature, except this one takes a random access iterator in, not just an input iterator. And here in the body, we just do one O of 1 operation that jumps the iterator forward. So what happens when we call advance? So say we have a call to advance, takes an iterator I, and then some step count n. Now, if I is, say, a linked list iterator that's only bidirectional, we look at the two advance overloads. We see that the first one works. Every bidirectional iterator is an input iterator. Okay. The second one does not work. A bidirectional iterator is not random access. You can't jump around a list. So in this case, only the first advance overload works. We pick that overload, and we get O of n time. Question?
Is this technique where you're putting the concept name as a template declaration equivalent to using a where clause?
I'm sorry, could you repeat that?
Sorry, is it when you write like input iterator up there, is that equivalent to just writing where input iterator?
This is a shortcut syntax that's very convenient for a lot of short examples. So saying input iterator of iter here is exactly identical to saying type name iter where input iterator of iter. Now, what if in this advanced call we have a vector iterator? So I is a vector iterator. Is that an input iterator? Absolutely. Yes, it is. Is it a random access iterator? Yes, it is. So now both of these advanced functions match. How do we pick the better one? So concepts have partial ordering rules that allow you to choose the bottom, the faster advance, over the top. Now, why is the bottom one better? Why is it more specialized than the one on the top? Well, remember, every random access iterator is an input iterator. But the converse is not true. Therefore, this algorithm works on more specialized types, random access iterators, than the top one. It's therefore preferable. So when you call this with a vector iterator, you'll get the fast O of 1 behavior.
Is there a way to explicitly specify that you would like the more general form or some other form of the specialization used? Like saying advance, and I want you to use the input iterator form even though you could use the random access one?
It's a possibility. We have a syntax for it.
I'm mainly thinking of this in the case where you have something analogous to multiple inheritance and the compiler can't choose what the best specialization is to use.
Sure. There's other ways to, I'm not going to go into them in depth, but there are other ways to help direct this so that if you do have an overload set that can be ambiguous, you can help push the compiler so that it always does the right thing.
So if random access iterator were defined first, and then somebody came along and wanted to define the input iterator class,
Sure.
that would make this work, how would you do that?
You could do that. What you would do, you actually use the concept maps feature, which will go into a little bit more depth on concept maps. And you can state that even though input iterator and random access iterator are essentially separate in that case, because they came in at different times, maybe even from different libraries, you can still say that every random access iterator is an input iterator, but the converse is not true. We'll show you that, well, very soon. But to really talk about concept maps, we're actually going to look at another critical C++ OX feature, which is a for each loop. So one of the things that's actually hard to do with STL containers is just looping over the elements. It's not hard, it's regular, you always do the same thing, but it takes a lot of writing. You have to access the nested iterator types, you have to call begin and end and loop over these iterator loops. What you really want to do is just say, for every v in values, do something. Right? Simple and direct. A lot of other languages have this. And the key to writing this feature, to adding this feature into C++ OX, is how do we make it work for all the containers in the standard library, plus all of the things that users come up with that they actually want to iterate over. So Python has an answer to this. It's the iterator and container protocols. C# has an answer through the IEnumerable interface. And C++ OX with concepts has an answer. It's concept maps. To see how this works, let's look at the underlying concept, which is called for each loop. So in this concept, we want to describe what it means to be able to iterate over something. That something has type X. So we have an associated type called iterator that is an input iterator. And now from the container or whatever we're iterating over, we have begin and end functions that return iterators to the beginning and ending of that sequence. Very simple. Now what's going to happen is this is a concept defined by the C++ standard, and we're going to define a translation semantics from a for each loop like this down to an actual use of the for concept to write the kind of loop that you're more familiar with. Okay, so here we take just a loop over the vector of integers called v. And what we do is we go through the for concept to access an iterator for that vector, pull out the beginning and ending iterators, and iterate over those. And then here's the body of the user's loop, where we actually create the variable I that the user asked for up here and print out the value. So this is a simple translation semantics. What it does is it expresses this new for each loop through the concepts mechanism so that users and the library can tell the compiler how do you iterate over certain things. For example, let's iterate over built-in arrays. Should be relatively easy, right? Well, what do? We need some primes, which is an integer array, to meet the requirements of the for concept. We can do this with a concept map template. So here we have a concept map for the for concept. It says that any array whose element type is t and has n elements in it meets the requirements of for, and here's how. The iterator is a pointer to t, and the begin and end functions return the beginning of the array and one past the end of the array. So just having this concept map in here, which hasn't changed the concept at all, hasn't changed the built-in array types at all, makes it possible to iterate over all built-in arrays using this for each loop.
But you can't iterate over a const vector this way. The iterator type won't match.
You can't iterate over a const vector with this, no. We can map for, here's for non-const vectors. So say we want to iterate over vectors, which is our original example. We write another concept map that says vector of t meets the requirements of the for concept. The iterator that we use is the vector iterator. And the begin and end functions in the concept map forward through to the member functions begin and end inside the vector. Again, we haven't changed the vector to do this. Now, if you'd like to do this for a const vector instead of a non-const vector, we would have the for concept map on const vector of t. We would pass in const vector of t references into begin and end, and then the iterator specified here would be the const iterator of the vector.
I'm confused about the namespaces.
Sure.
Why do you need the type there? Wouldn't you just need the type name iterator semicolon? What's going on there?
What's going on here is that the concept map is intended, it has to supply all of the requirements of the concept. Now the concept requires an associated type called iterator that is an input iterator. And so in the body of this concept map, you need to provide a type for that iterator via typedef. Now the type can come from anywhere. In this case, it comes from inside the vector because you're typedefing it from inside the vector. But it could be anything else. With the arrays, we just said t-pointer is the iterator type.
So I'm just wondering, so there are two separate namespaces, one inside the concept map, which has a
Yes.
word iterator, and the one inside the...
Yes, there are two namespaces. Each concept is its own namespace, essentially. Right. And there are names within the concept that are specific to that concept. The reason for this is there can be many, many concepts all using the same names. They need to be separate. Otherwise, you get interfaces tangling with each other. Question?
So this for each construct presumably is something that's built into the language. And then is this, so that uses this for concept. So is this for concept then something that's built into the language?
It's built into the language or it's in the standard library, yes.
So in a sense, it almost seems like from looking at this, it seems like you can have concepts that are like fundamental to the language and concepts that are user defined.
Absolutely.
But how is it that like if it's in the standard library that it actually be used for something that's built into the language? I don't see how that would work.
Okay, so the concept itself could be defined in the language as in the compiler, or it could be in the standard library. Now, once that concept is there, the compiler itself can, of course, look up that concept and try to use it. So where the concept maps come in is that anyone, this would be the standard library, could introduce a concept map for that concept, because you're allowed to write concept maps for whatever concepts and types you want. And it's going to state that when you try to find a way for an array to meet the requirements of this for concept, here's how you do it. And it'll pick it up. Okay. Now, there's some facilities of the standard library that aren't containers per se. They're algorithms. For instance, there's the equal range algorithm on a multiset. And what that does is it searches for all of the values that are equivalent. So here we're looking for all the values that are equivalent to 17 in a multiset. What that's going to return is not a new container, but a pair of iterators. The first iterator points to the first value that's equivalent to 17, and the second iterator points one past the last value that's equivalent to 17. So say we want to just print out all the values that are equal to 17, right? We could do it with this loop. However, now we need to be able to iterate over pairs of iterators. How do we do this? Well, it's, of course, a concept map. So we want to say that a pair of iter, where iter is an input iterator, it meets the requirements of an input iterator, you can iterate over those. The iterator typedef is actually iter itself, and begin and end return the first and the second inside that pair. So this allows us to iterate over essentially abstract sequences into other containers represented via pairs. Now going further, we have to write a lot of concept maps for the standard library. For instance, we want to be able to iterate over vectors, lists, decks, maps, sets, multi-maps, multi-sets. It goes on and on. It gets a little bit tedious to write all of these for concept maps. But there's some commonality between all of these containers that we can exploit. There's a container concept already. It states what's the basic notion of a container, and part of the basic notion of a container is that you can iterate over the values, right? So here we're going to write one very, very general concept map that says that any type C can be used with the for each loop so long as C meets the requirements of the container concept already. And then in the body of this concept map, of course, the iterator that we use to iterate over the container comes from the container itself, the container concept, and the begin and end are going to pass through to the member functions begin and end for all of those containers. So this one concept map definition maps anything that is an STL container over into something that can be iterated on with this for each loop. So we're mapping essentially a full class of abstractions over to another abstraction with one concept map operation. Okay, I've talked a lot about the standard library. So the C++ standard library, especially the standard template library, was designed with generic programming and concepts in mind. They were all there. And then what happened is they essentially took those ideas and wrote them in documentation and then implemented using various template tricks to get it to work in C++. So what we need to do with the standard template library is we need to evolve it to use concepts. So we're going to take these informal specifications that they wrote down, the requirements on concepts, these are just documentation today, and turn them into real concepts, like the input iterator concept that we saw earlier. We also need to take the templates of the standard library, such as the find algorithm that we saw earlier. We need to give those constraints. We need to give them where clauses. So they're now within the template system. We get full type checking. And we also get more functionality. So concept maps give you functionality that we didn't have before. You can adapt syntax and say that my type here meets the requirements of this concept here through these syntax remappings. You couldn't do that before. So what happens when we evolve the standard library is we get the same library. It's going to work the same way. You'll use it the exact same way. Except you have more functionality, you have better error messages, it'll be easier to extend, and it'll be more sound and better specified. Now, backward compatibility is a huge issue. We're not talking about creating a new standard library. We won't do that. We're evolving the standard library in place, which means existing programs have to still work. If they work with the standard library today, they should work with the standard library tomorrow. This is particularly interesting when we're talking about extensions. So say someone has created their own iterator types. There's a protocol for that in the current standard template library. We're actually getting rid of that protocol and replacing it with concepts. Is this going to break all of the code that creates its own iterators? No, we can't do this. If we break code, programmers will reject this. So what we do is we actually write concept maps. And they're a little bit convoluted, but we write concept maps that can take the existing iterators that work with today's interfaces and seamlessly map them over into the new concepts library. So what happens when you take your old code and use it with the new concept-enhanced standard library is it's going to be doing these mappings behind the scenes that give you transition to the new concepts-based version. Let's take a quick look at error messages, because this is a big issue for a lot of programmers. So here's a really trivial bit of code that I absolutely love. All we want to do is call the sort algorithm on list iterators. So we want to sort a list this way. And the compiler helpfully tells us that we've made some kind of mistake. Helpful, right. So this error message is large. That's the first thing you see, and that's a problem, because there's a lot to paw through. If I gave you an example from a more advanced from a more advanced generic library, it wouldn't fit on this screen, it wouldn't fit in this building. So there's other problems in here. Look at all these function names in here. Double underscore insertion sort, double underscore final insertion sort. The user never called these directly. These are implementation details that are leaking out to the user because of the way the template mechanism works today. So if we back off and now use a different compiler, we're going to use concept GCC, which is our implementation of the concepts mechanism in GCC with its new standard library. When you try to make this call, you're going to get a much friendly error message. So this error message is going to tell you, at the point where you made the call, not in the library implementation, that there is no sort that you can call with list iterators. Why is there no sort? Well, there's a candidate here. There's the standard sort. that almost worked, except there's no concept map that makes a list iterator into a mutable random access iterator. In other words, you've failed the requirements of this sort routine. Therefore, it's not going to try to instantiate it. It's not going to let you make this call. If you can write a concept map that makes a list iterator into a mutable random access iterator, then it'll let you through. On the other side, here's a simple count algorithm. And I'm going to make the same mistake here that I made last time. I'm going to use less than to compare iterators. But these are input iterators, so it doesn't work. Now, if there are no where clause, there are no constraints on these, then the compiler would accept this and it would fail if you try to use list iterators. Same problem we had at the beginning of the talk. Now with concept GCC, we get full type checking of the count algorithm when we define the algorithm. And what the compiler is going to do here is when it type checks, it's going to look for a less than operator that takes 2 iterators, first and last. It'll see, wait, there is no less than operator defined in the input iterator concept. This is an error. It'll produce an error at this point. Now these two sides, the user side we saw first and the template author side that we saw here, that's modular type checking. And together they make templates much, much easier to use because you're getting the full capabilities of the type checker as soon as you write your template. You don't have to wait till later and test with a huge number of types to make sure that it's going to instantiate properly.
You have a syntax error, of course, too.
Where? Oh, yes, I do have a syntax error. There is a stray close squiggly. My apologies. It's historical. So, to wrap this up, concepts is not the work of one person, it's the work of many people, and you may recognize some of the people up there. The 2 universities that are doing much of the concepts work are Texas A&M University and Indiana University. And if you're interested in concepts, let's bring this around to a summary. What do concepts do? They provide complete support for generic programming. All of the ideas of generic programming can be expressed directly in C++ when you're using concepts. And they're easier to use. They throw out a huge number of template tricks that we're used to playing with in the C++ world. If you don't need them, just express them directly using concepts. Now, if you want to try this out, if you're really interested in concepts, you want to try them, I encourage you to go get concept GCC. Here's the URL. There's binaries for several platforms, source code to the compiler, whatever you want to play with, and try the implementation. It supports almost the entirety of the proposal. It has a concept enhanced standard library, so you can see the error messages and play around with concept maps. And this is all intended to go into the upcoming ISO C++ standard, just dubbed C++ OX. So the whole concepts feature, concept maps, including the for each loop, should all be part of the next C++ standard, along with an upgraded standard template library. And we're hoping that this will make generic programming more accessible and more widely used. Thanks for your attention. Can I answer any questions? Wow. We'll go this way. Sure, go ahead.
So you showed the equality comparable concept earlier.
Yes.
And it requires both a double equals and a not equals operator.
Yes.
It's a pain to write that not equals operator because it always has the same definition. Is there a way to automatically generate all of those?
Yes. A couple options. So one, there's a default implementation that you can put into your concept. That'll let you express not equals in terms of equals. The other option is that there's this thing called standard relops. Right? Horrible abomination because it didn't work. It actually works with concepts because you can constrain those operations appropriately and not instantiate them when they won't work. So yeah, there's multiple answers. Sure.
When you defined a concept earlier, you had axioms.
Yes.
What are those? Are those just, is that something I can check, or is that just for the...
It's something that can be checked. So it describes the properties of these types. And there's a lot of ways you can use them in compilers. For instance, you can use them for optimization. So if you know the premise of the axiom is satisfied, well, you can possibly do rewrites and transforms on your system to use a more optimal version. You can use them for verification if you have simple axioms, right? A compiler might be able to verify that, yes, indeed, you do meet these requirements. The most interesting thing, I think, is that you could use them for testing. If you've said that your type meets the requirements of a concept and there are axioms in that concept, you can treat the axioms like a verification tester. And if you can synthesize values of that type, you just send them through essentially the assertions in the axiom to make sure those axioms hold. And you can do spot checking. And essentially, it's another form of unit test.
What language are the axioms written in?
They're written in a very simplistic form. It's not C++. It's essentially just expressions and if statements.
Is it Turing complete?
Oh, no. No. That would be a mistake. Very, very simple. Just think ifs for conditionals and equality statements. That's essentially all there is.
So the concept maps, as you presented them, provide a good way of mapping like an existing concrete definition, like say the existing vector,
Yep.
and some sort of concept of the vector that holds for the vector, and the concept map tells you how those map to each other. But is there a way to say write a new vector or some other new class and directly say at the time that you write it, this implements these various concepts, and here's exactly how I map my types without having to write both my type name iterator inside the class and then write also a concept map for my class that says, oh, my iterator is this iterator. Can I just say, here is my vector iterator.
I see what you mean. Yeah. We don't have a special shortcut syntax for doing that. Right now, the way we tend to do things is we just write the class, and then following it, we write several concept maps to state what it should do. And in fact, the concept maps are fully type checked when you write them, so it'll verify that you actually do meet the requirements of those concepts.
Because it seems like if you have that sort of shortcut, most of the STL could be condensed into just the concepts. And then the containers themselves would be very bare bones wrappers of, I implement all these concepts and a few specific names, and that's pretty much it.
Yeah, it could provide some shortcut. Yeah, we don't have a syntax for it, essentially, but the idea is sound. Yeah. Was there something back here? Nope. Okay. Go for it.
Yeah, the implementation that's working, have you seen what the compile time increases are?
Yes. So we're doing a lot more type checking when you look at a template. And today's template processing is essentially a weak syntactic check. It doesn't do very much work. Now we're doing full semantic checking. That's going to be more expensive. Now, in our prototype, it's much more expensive because we have a very poor implementation of a certain feature of concepts that slows down the compiler by a factor of 10. We know how to fix this. We're working on fixing it. Of course, we haven't done it yet. So we expect there will be some impact on compile time performance, but you're also going to be getting a huge reduction in the amount of code that's actually required to implement a template library, because all these template tricks, they take a lot of code. Okay, thank you very much. If you have any other questions, feel free to email me or whatever. Thanks.